Exploring Venus, hopping probes, and leaping robots. This week on Planetary Radio. I'm Sarah Al-Ahmed of the Planetary Society, with more of the human adventure across our solar system and beyond. This week, we're back with part 2 of our special coverage from the NASA Innovative Advanced Concept Symposium, a place where today's wildest ideas may become tomorrow's missions. We'll start off with Mary Knapp, a research scientist at MIT Haystack Observatory, whose Great Observatory for Long Wavelengths could open an entirely new window onto exoplanets by studying radio waves that are too long to detect from Earth's surface. Then Michael Hecht, also from MIT Haystack, and principal investigator for the MOXIE experiment on NASA's Perseverance rover, shares how his team's exploring Venus with electrolysis concept could turn the planet's dense atmosphere into fuel for flight and scientific discovery. We'll also hear from Benjamin Hockman, robotics technologist at NASA's Jet Propulsion Laboratory, whose Venus Balloon Observatory concept and Gravity Popper's asteroid probes could change how we explore our planetary neighbors. And finally, Justin Yim, assistant professor at the University of Illinois Urbana-Champaign. He'll take us to Saturn's moon Enceladus, where his team's legged exploration across the plume, or LEAP robot, could literally hop through the icy geysers to learn about the world's subsurface ocean. Then we'll check in with Bruce Betts, chief scientist at the Planetary Society, for What's Up. If you love Planetary Radio and want to stay informed about the latest space discoveries, make sure you hit that subscribe button on your favorite podcasting platform. By subscribing, you'll never miss an episode filled with new and awe-inspiring ways to know the cosmos and our place within it. Right out the gate, you'll notice that I'm a little hoarse today. That's because I spent the weekend at TwitchCon, sharing the love of space exploration with people and being on a panel with Moo Hoodles. I'll share that adventure in a future episode, but bear with me because I might sound a little bit hoarse. Each year, NASA brings together researchers and entrepreneurs to share their progress at the annual NIAC Symposium. This year, it took place on September 9th through the 11th in Philadelphia, Pennsylvania. I've had the privilege of hosting their webcast for the last 3 years and getting to meet all of the different NIAC fellows. The people you'll hear from in this episode are part of larger teams that are developing these bold early-stage concepts. Our first guest is Dr. Mary Knapp, a research scientist at MIT Haystack Observatory. Her team's project, called the Great Observatory for Long Wavelengths, or GOLO, envisions a constellation of thousands of small satellites working together as a single giant radio telescope, one that could finally let us observe the low-frequency signals from the universe and help us explore exoplanet magnetic fields. That would give us a whole new way to learn about the habitability of these worlds and how they interact with their stars. I'm here with Mary Knapp from MIT Haystack Observatory with a project called GOLO. So that's the Great Observatory for Low Wavelengths. So first question, why is it that we haven't actually managed to get good observations of the low wavelength universe?
Yeah, so it's our Earth's atmosphere, or more specifically the ionosphere, which is the upper part of the atmosphere where atoms and electrons are separate. So that part of the atmosphere blocks long radio wavelengths, much like the lower atmosphere blocks ultraviolet wavelengths or X-ray, things like that. So it's our own planet that prevents us from seeing this part of the universe.
But in the tradition of the great observatories, Hubble, Chandra, Spitzer, Compton, we usually launch those out into space. So what's preventing us from doing that kind of thing with this specific wavelength range?
Yeah, the challenge here is the long wavelengths. So these waves are meters to kilometers in length. And when you build a telescope, a space telescope or a ground-based telescope, your telescope needs to be many wavelengths in size. So that becomes very difficult when your waves are a kilometer. So suddenly you need a telescope that's many kilometers in size, and that is a very difficult construction project. So that's why we have not yet built a telescope for these wavelengths, because it needs to be really big. Luckily, we don't have to have that telescope be a single piece. It doesn't have to be a single dish. We can break it up into lots of little pieces in kind of like a cloud, and all those pieces can work together to make a virtual telescope.
Well, we've already heard over the last day some great solutions for ways that we could build really large-scale structures in space, but that is super challenging. So I love this idea of creating this constellation of these observatories and maybe using interferometry. Can you talk a little bit about how you can, use this many spacecraft all at once to act as one giant telescope in space?
Yeah, so that is the main challenge that we are working on solving in our NIAC study. So coordinating thousands of spacecraft is hard. It is something, though, that the commercial industry is starting to do, particularly the Starlink constellation and similar communications constellations. There are many thousands of spacecraft, and they're coordinated. Interferometry is kind of an extra challenge beyond what industry is doing, because you need to know the positions of every spacecraft very, very, very precisely so that you can phase up their signals, so that you can make sure all the waves that are coming into the telescope are measured with very precise timing so that you can line them up. And it's that lining up of the phases of these waves that allows you to make this virtual telescope. And that's challenging, but we think tractable in the not too distant future. Our constellation will be much farther away than Starlink, so you might see the launch, but then the spacecraft will go far away to what's known as the Lagrange point, which is a special point in space where gravitational fields from the Earth and the Sun, they kind of balance. And so if you go to this place, called L4 in our case, you can put something there and it will basically stay where you put it, which is not so common in space. Things tend to wander off. What we want to do is send many, many spacecraft to these Lagrange points, and then they will just stay there and, wiggle around a little bit, which is convenient for the type of science we want to do, but they won't wander off and they won't cause any space debris issues for the Earth, which is really important.
Now you say many, many of these. How many are we talking here?
So ultimately, we want to work up to a constellation of 100,000 spacecraft. Yeah, it's a large number. It sounds scary. But the good news is that there are many steps along the way with smaller numbers that still will do really exciting science. Because this part of the spectrum is so unexplored, there is a lot to learn even with smaller constellations, even with 5 or 10 or 100. There's new science to do. We'll see the universe in a new way. We'll make maps of the sky that we've never had before. And as we build up to larger and larger numbers, our sensitivity improves, our resolution, the crispness of the image improves. And ultimately, the goal is to be able to measure signals from exoplanets, which is what we need the 100,000 for.
How big are you envisioning that this constellation would be?
So about 6,000 kilometers in diameter. So kind of like think about a cloud that's about 6,000 kilometers in diameter. That's pretty big, but space is also very big. So there's plenty of room out at L4 where we want to go for a constellation that size. And we have some clever orbital designs that we think will prevent any collisions between spacecraft. So it's big, it's a lot of spacecraft, but we've done enough work that we think this is possible.
Usually when we're talking about great observatories, they are one giant structure. But because you're talking about a bunch of tiny spacecraft, you now have this redundancy, essentially. How does that allow you to not worry as much about, all these points of failure? And have you done any simulations on how much can fail before the whole thing doesn't work anymore?
Yeah, so we think this is one of the kind of game-changing features of GOLO, is that it is massively redundant. You can lose a few here and there, and then they can redistribute tasks amongst themselves and continue operating. And you can send more. That's the key. With JWST and some of these large observatories, they're not designed for servicing. They're not designed for an astronaut to go and fix them like Hubble is, and that's because they're far away, and it would be challenging to get someone out there to do the repair. In the case of GOLO, we don't have to send anybody, but we can send more components. We can send more satellites, more LNs, more CCNs, and they may be upgraded. As technology improves, we can send new, better spacecraft, more capable, better processing, maybe improved antennas, more storage. So the constellation can upgrade over time rather than being kind of a fixed technological point.
We haven't spoken yet about why this particular range of wavelengths is so key for our understanding of the universe. You brought up exoplanets earlier. What is it about exoplanets that we could learn from these low wavelengths?
So the key thing about exoplanets that I've always been interested in, like my whole career so far, are magnetic fields. So we have a magnetic field on the Earth. It does protect us from some cosmic ray impacts, and so when astronauts go outside of it, they're actually at risk of radiation harm. So our magnetic field is a really important feature of this planet. We know that our sister planet Venus does not have a magnetic field, at least today. It may have in the past, but we don't know. What we don't really understand from the small number of planets we have in the solar system is how common it is for a planet like Earth to have a magnetic field. And we think that at the very least we can say it matters for how an atmosphere evolves, whether a planet has a magnetic field or not. So this is something we'd really like to learn about exoplanets. Number one, so that we can understand whether or not they might retain atmospheres and potentially be habitable, but also so that we can understand more generally, how do planets work? Which planets have magnetic fields? What do they look like? How long do they last? Things like that are just sort of fundamental science that we want to do. Planets with magnetic fields have this nice property that they emit radio waves. They emit radio waves from electrons that spin around their magnetic field lines, and they kind of scream out into the universe as they do that. So the Earth emits radio waves, Jupiter and Saturn and Uranus and Neptune all emit radio waves at low frequencies. The frequencies where this emission happens, it's directly proportional to the magnetic field strength. So a stronger magnetic field emits higher frequency radiation. So Jupiter has the highest frequency emission of this type in the solar system. Earth is at a much lower frequency. We can't even see our own radio emission through the ionosphere on Earth. We know it's there because of spacecraft, but we can't see it from the ground. So we know that for planets that have magnetic fields like the Earth, if such planets exist, we need to go to space to see that kind of radio emission. And we'll be able to measure the magnetic field strength of these planets remotely with radio techniques. And that's one of the big motivations for GOLO, is to be able to look around our solar neighborhood and measure the magnetic fields of the planets and put those in the context of exoplanets more generally, and maybe learn something about habitability.
Honestly, this is one of the, I think, the key missing parts as we're, particularly delving into the search for life in the universe. Now that we have things like JWST that can tell us, kind of the atmospheric composition of these worlds, and we're getting closer and closer to these direct images of smaller Earth-like planets. But even then, without a magnetic field, who's to say that they're habitable? So we can look at these systems and learn so much, but this is a key missing point that I think a lot of people aren't really considering as we're doing the search for life work.
Yeah, and it's a hard remote measurement to make. There are other techniques that potentially could allow you to infer magnetic field through some modeling approaches. The radio emission is pretty straightforward. You observe radio frequency emission within this low frequency part of the spectrum, and you can pretty directly say what the planet's magnetic field is. And that's a really valuable tool that it would be really nice to have in our toolbox to add to the complex picture of habitability that we're developing for exoplanets.
Our next concept is going to take us somewhere much closer to home. Dr. Michael Hecht is also a research scientist at MIT Haystack Observatory, but also the principal investigator for the MOXIE experiment on NASA's Perseverance rover. He's leading a NIAC study called Exploring Venus with Electrolysis, or EVE. His team is developing technology that could help us extract oxygen and carbon monoxide directly from Venus's thick atmosphere, providing power, propulsion, and even buoyancy for long-lived balloon explorers that could study our sister planet from within its skies. Here we have an interview with Mike Hecht from MIT Haystack Observatory. Earlier today, I spoke with Mary Knapp, who also worked there. But your presentation, which was yesterday, was the EVE project, Exploring Venus with Electrolysis project. It's interesting to me because you're also the PI of MOXIE on the Perseverance rover, right? Which is the Mars Oxygen In Situ Resource Utilization Experiment. Did I get that right?
You got it right. That's right.
But that one also uses electrolysis. Was that part of the inspiration for how you came up with this project for Venus?
Well, in fact, that was very much part of the inspiration. And, the realities of working on these big projects is that they end someday. And when they end, you're sitting there with all this knowledge, with all this know-how, with all this physical capability, instruments, laboratories, and you say, what do I do with it next? Okay. In this case, just serendipity. I worked at JPL for 30 years before I came to MIT Haystack, and I ran into an old friend, Jim Cutts, at a conference. Jim has been working at JPL with an emphasis on Venus for quite a few years. And in the last, I don't know how many years, his passion has been ballooning in the middle atmosphere of Venus. And he pulled me aside and said, we have all this technology for doing ballooning. The biggest problem we face is that balloons only last a couple of months and the helium leaks out and they fall, in the case of Venus, they fall below the clouds and burn up. We could combine our technology with your technology and do something really exciting, which is to have a long duration balloon. So honestly, I give Jim full credit for this idea. All kinds of lights went off and said, exactly, this is what we need to do, from my point of view, to keep progressing with MOXIE and the MOXIE technology. And as time has evolved, I'm at least as excited about this application as I was about MOXIE's original intention, which was to help bring forward the day when we actually send humans, our grandkids, to Mars.
Why is it particular that you're trying to target this middle atmosphere on Venus for this kind of research?
If I were going to go to one of these planets, I would rather go to Venus for a sky cruise. Okay, and here's what I mean by that. The surface of Venus is, to say the least, inhospitable. At 50 to 60 kilometers, there's a cloud layer. It's mostly sulfuric acid, but very, very, very dilute. I mean, honestly, if this room was filled with an aerosol of sulfuric acid, like the cloud layer, it would be uncomfortable, but it wouldn't, you wouldn't be dissolving your skin. So in addition to being a lot less hot. In fact, it's a shirt sleeve environment. It's roughly the temperature of this room, roughly the pressure, if not of this room in Philadelphia, maybe a room in Denver. It's very comfortable for humans. You could go outside and feel the wind in your face. You can't breathe the CO2 atmosphere, and you need some protection from the sun and from the mist. So you need some skin cream and some eye goggles. But honestly, it's no worse than scuba diving, right? Or in terms of the protection. We're not talking about a big pressure suit like you need on Mars. You have radiation protection from all that atmosphere above you. So that zone, 50 to 60 kilometers above the surface of Venus, would actually be a rather nice place to visit on a sky cruise, and you could do parasailing and all kinds of fun things and watch the surface go by if you have the right instruments. Of course, you are in a cloud bank, but there are instruments that can see through that cloud bank. So that's all fun, and maybe that motivates why we study it. But in fact, if you have an Earth-like atmosphere, that also suggests the possibility of habitability, and certain researchers such as Sarah Seeger have looked at this carefully. There's nothing equivalent on Mars that you could say an Earth-like organism could live in today. Maybe even a plant could live in today. Does anything live there? Well, we can't rule it out. It's certainly possible. And scientificically, the ability to study this crazy dynamic atmosphere itself, which actually blows you around the planet every 4 Earth days because it's 200-mile-an-hour winds are carrying this balloon around. It's dynamic, it's complex, chemically complex, and in addition, astonishingly, you can study the subsurface of the planet from a platform 50 to 60 kilometers up with something called infrasound, which is a way of doing seismometry by looking at the seismic waves propagating through the atmosphere. So it's an incredibly capable scientific platform. It's sort of home base for where you could do things like go down to the surface and collect samples, or in terms of the NIAC, phase 1 projects, there's another one by Ben Hockman here who's saying, hey, just hang a tether a few kilometers long below the cloud layers, and then we can get a clear view of what's underneath. So it's your home base. It's your home. You can send up drones. You can do all sorts of things once you have a home base. And the key to that, of course, is keeping the balloon aloft. And I don't think I've closed back on how you do that and why MOXIE is involved. And the way you do that is you take advantage of the fact that it's a carbon dioxide atmosphere, not oxygen and nitrogen like we have here on Earth. And carbon dioxide's substantially heavier than oxygen because it's an oxygen molecule with a carbon atom added. It's heavier. And so oxygen itself is buoyant on Venus. Carbon monoxide is buoyant on Venus, and those are the two gases that MOXIE produces. So just by running MOXIE alone, modified from an engineering sense so it will work on Venus, we can generate buoyant gases directly from the atmosphere. And by the way, there's lots of solar power on Venus. It's actually closer to the sun. And to make it easy, from an engineering standpoint, the light is very diffuse because you're in a cloud. It's very bright, it's very diffuse, but it doesn't matter where you point your solar panels. You can point them up, you can point them down, forward, backward. You can have solar panels on both sides. They will collect the same sunlight. So for 50 hours or so, you can collect sunlight, and then for another 50 hours, you'll traverse the far side of the planet, and you need a method, batteries or some other method to store some of the power collected in the daytime. It turns out MOXIE also offers you a path to doing that, because if you change the polarity of the voltage, in other words, instead of negative, you go positive, you can collect power. MOXIE becomes a fuel cell instead of an electrolysis system, and you can collect power from it by reacting the carbon monoxide and the oxygen that you produced in the daytime. So without having to add a new device, a new instrument, you can actually turn MOXIE into a battery to get through the night side transit. So this is, just all karma in a way, that there's two projects that can come together to do something that is so well suited to studying the atmosphere of Venus, to studying the surface of Venus, to even make a platform for future human exploration. It's really, really exciting.
Are there any things that you think are up in that atmosphere that might hinder this balloon system or degrade it over time, even if you have this fuel and energy available?
We do have to deal with sulfur compounds. I mentioned the sulfuric acid. By the time it gets into MOXIE, which operates at high temperature, it will have turned into SO3. And in fact, there's a lot more SO2 than SO3. And that could potentially be hazardous for the materials in the MOXIE system. So right now we're looking at what the sensitivity is of those particular kinds of cells and stacks that we use to sulfur compounds. Other than that, it's remarkably benign. It doesn't offer a lot of the hazards that Mars poses, which might be dust, which might be temperature swings day and night. It's a very gentle place.
How does this electrolysis actually work? Just briefly for people who aren't familiar with the process.
Right. Electrolysis, well, it is, I mentioned fuel cells. It is the opposite of a fuel cell. And what that means is that in this case, you would introduce carbon dioxide. In more common cases, you start with water to do electrolysis. You introduce carbon dioxide. It hits this very hot, very specialized membrane where catalytically, essentially, it's separating the CO and the oxygen. So that's the first step. So you get an oxygen ion, a carbon monoxide, molecule. The carbon dioxide molecule just goes out the exhaust with whatever carbon dioxide you didn't react with, but all the magic is in the oxygen ion, which now is drawn through a special ceramic membrane by an applied voltage. And on the other side, it's an oxygen ion, so it finds a partner and becomes O2, the oxygen molecule, and that comes out in an ultra-pure stream on the far side of the membrane. That's exactly how a fuel cell works, except the fuel cell works the other way. Instead of putting in electricity and carbon dioxide, you put in carbon monoxide and oxygen, and you get out electricity. So you just run the film in reverse, and you've got a fuel cell. That's how it works. Electrolysis itself is a fairly common technology. Even solid oxide electrolysis is fairly widely used, but adapting it was a real heroic undertaking.
Our next guest is Dr. Benjamin Hockman, robotics technologist at NASA's Jet Propulsion Laboratory. He's actually working on two separate NIAC projects. One of them envisions another way to look at Venus, using balloon-borne observatories in the atmosphere, while the other one, called gravity poppers, would send swarms of tiny hopping probes across asteroids and comets to map their hidden interiors.
I'm here with Ben Hockman, who is a robotics technologist at NASA's Jet Propulsion Lab. We're pretty much neighbors.
Yeah, up in Pasadena.
Well, you're here with not just one, but two projects. We heard a little bit about one of your projects yesterday, which we'll talk about now, Gravity Poppers. That's a phase 2 project, but later on today, after this break, you're going to be sharing a little bit about Tobias, another project that's in phase 1, yeah?
Yeah, they couldn't be more different, but they're on two sides of the spectrum of robotics that I really love to work on. Yeah, the first one I talked about yesterday is all about understanding the interiors of asteroids, and then the one I'll talk about in the next session is about, seeing the surface of Venus.
So I think when a lot of people envision this idea of asteroids, right, a lot of it connects to their idea of asteroids plowing into Earth, these solid, rigid bodies that are like dangerous to us. But as we've been going out there and exploring more of these objects, we're finding that they're more rubble pile-y, or there are some that are solid metal. There's so much variation in this. So what inspired this idea of the gravity popper to help us understand more about their interiors?
Yeah, so the small bodies are really enigmatic. Like, we really don't know a lot about them. We have sent some dedicated missions to a few of these bodies of different types. There's some potentially hazardous near-Earth asteroids, like the target of OSIRIS-REx's mission, Bennu. But then there's more main belt comets and distant comets and even interstellar objects. They're all small, but they have one thing in common. We really have difficulty deploying traditional methods to look inside the bodies. And especially for planetary defense, like you're saying, it really matters in terms of the kinds of deflection methodologies we might consider for disrupting or deflecting these asteroids off a critical path sometime in the future. What their internal structure is. If we hit them with a big impactor, will they break apart completely? And we really don't know much about their efficacy without knowing a little bit more about their internal composition and structure. And so Gravity Poppers was kind of this out there idea of using a non-conventional way of kind of really probing the interior structure of these bodies.
How is putting a bunch of tiny little hopping devices onto one of these asteroids or comets or interstellar objects a way for us to probe the interior? And if you'd like as well, I know you have a model of this thing that you can show us, if you would like to pick it up and share.
Yeah, it's a little hard to wrap your head around, but yeah, as it turns out, hopping around an asteroid with these can actually help you learn about the interior structure. And to take a step back, there's kind of three classical ways we learn about the internal structure of the Earth and also other planetary bodies. There's radar measurements, which kind of emit and then listen for the reflection of radio waves, and you can kind of get a sense for the layers. There's seismology, which has really helped us understand a lot about the deep interior of Earth and the way that, waves reflect during earthquakes especially. And then there's gravity science, which is a little bit out there because it's really probing directly at the mass distribution of a body. We really take it for granted that gravity is down on Earth, and for all intents and purposes, that's fine for all of our everyday needs. But it turns out every mass attracts every other mass, as Newton predicted. And if you have a sense enough instrument in orbit around a body, like, for example, the GRACE satellites around Earth or the GRAIL satellites around the Moon, you can really be sensitive to all the very fine perturbations in the gravity field and then infer mass variabilities on a much finer spatial scale with inferring those anomalies. Well, on asteroids, that's very difficult because it's hard to get very close to the body. OSIRIS-REx was the lowest orbit of any satellite, and even it was hundreds of meters or many, like a couple body diameters away from the body. And it turns out that's very difficult to be sensitive to those high-order gravity terms that essentially come from the small voids under the surface or rocks of certain anomalous densities on the surface, unless you get really close. And so we were thinking, how do you get really close to the body? And it turned out OSIRIS-REx also discovered rocks being ejected from Bennu. And scientists were actually able to track those rocks as they flew around the body and recover a higher resolution gravity model and make inferences about the internal structure just based on those natural particles. But there were a lot of challenges with that approach. This would inspire the Gravity Poppers, which is essentially an artificial version of what OSIRIS-REx discovered on Bennu. And by taking our own probes, such as this prototype, which is a 5-centimeter cube, and deploying them to the surface of the body where they would bounce around randomly and then hop once they came to rest, we would be able to get these very low altitude measurements by tracking their motion. So a mother spacecraft keeps a safe distance, doesn't need to get close to the dangerous asteroid, but by watching the kind of chaotic nature of dozens of these probes as they bounce around the body, it's able to make these inferences about a very high resolution gravity field and then infer what's inside the body.
Now, I remember that moment when the OSIRIS-REx mission went in to try to grab a sample that tagged SAM and almost buried itself in that object. These are a lot, they're very small, but are you concerned that as they're hopping around these objects, particularly these rubble pile asteroids, that they might embed themselves in the subsurface?
Yeah, they certainly will kick up some debris. We do expect that many of these, at least the near-Earth asteroids, are covered in rocks and loose rubble, and so when they impact the body, they will kick up some debris. We will equip these with some very elastic appendages so that it helps them to bounce away when they do make contact with the bodies. The reason we bring dozens of them is one for spatial coverage, but we also aren't sensitive to losing some from time to time, and we actually do expect some of these to either get embedded in the surface or even escape the body. Turns out the escape velocity on these bodies is on the order of 10 centimeters per second, so very slow. And if you're not careful, you can actually hop away from the body and just fly off into deep space. So because we're taking many of them, we can be robust to those sorts of uncertainties and still get good science. And we're in our phase 2, we just scratched the surface in phase 1, and there are so many parameters and considerations to study. So phase 2 is really going to be our opportunity to really drill down and answer some of these questions with more high fidelity simulations and experimental testing and reduced gravity test beds about, what is the nature of the impact of these as they bounce around on the body, and ultimately, what kind of gravity field can we expect to recover from this kind of observation.
Well, looking at it, it's kind of like a cube with some spikes coming out of each of these vertices here. How does it actually hop?
Yeah, it turns out you don't see the hopping device because it's inside. And this is a concept that was actually proven on some hoppers that were deployed on Hayabusa 2, a Japanese mission to the surface of asteroid Ryugu, which is a 1 kilometer body, very small. But there was a Minerva, I forget the acronym, but it was a JAXA small rover about this big that also had an internal reaction wheel. And a German space agency, DLR, contributed a platform called Mascot, which was a bigger box that also had an eccentric mass inside that it could swing, and by swinging an internal momentum device, you can actually change the momentum of the chassis, and because these spikes are in contact with the ground, it's able to rotate and essentially hop. It's not the most efficient process, but in microgravity, you only need a very small kick in order to get into really high suborbital trajectories.
We could talk about this for a long time, but I want to get to your other project just briefly, since you're going to be presenting about this Tobias in a little bit.
The basic idea is it's very difficult to study Venus because of its harsh environment. The surface is at 500 degrees Celsius, it melts aluminum, and so we're really having trouble designing long-lived platforms for getting on the surface or at least below the clouds. However, people have been developing high-altitude balloons for a number of years, and these concepts have gotten quite mature. The idea is there's a Goldilocks zone in Venus's atmosphere that's not too unlike Earth's atmosphere in terms of temperature, pressure, and the conditions, where a balloon with an instrumented gondola, or the payload under the balloon, could kind of comfortably sit in the 50 to 60 kilometer altitude range. The problem is there's still a global layer of clouds below that altitude where it gets real hot and uncomfortable to design a balloon to fly down to those altitudes. So there have been a number of ideas of how do you actually get below the clouds, because of course what scientists would really love is to take pictures of the surface invisible. We kind of forget sometimes whenever you see a picture of Venus, you're usually looking at a radar image. You're not actually looking at a visible image. If you look at Venus in the visible, all you see is a bunch of clouds. And that really matters because a lot of the mineralogy and geology of the surface can only really be revealed if we see it in visible and near infrared wavelengths. So the only way to do that is to get below the clouds. And so our idea is to extend the reach of this gondola without having it need to go below the clouds by dangling essentially a very long tether, and on the end of it would be a camera inside of what we call a tow body. The tow body is dangling below, and because the way Venus's winds work, the balloon is drifting with the prevailing winds at its altitude, but at this lower altitude there will be some what we call wind shear blowing against the body. So it's kind of being dragged along across the surface of Venus, and as it does so, it takes consecutive images in the near infrared spectrum of the surface where it can stitch those together and create a very high resolution mosaic of the surface of Venus as the balloon circumnavigates the planet about once a week.
This could answer so many of the issues we're having. And I spoke yesterday with the team from EVE that was trying to use electrolysis to power something that could float exactly about in this layer of Venus's atmosphere. What is your team's idea for how you're actually going to be powering this device?
The powering devices, that is one of our main areas of study in the phase 1. There's a few options. We do have the ability to have onboard power generation on the tow body itself. In the daytime, we can put solar panels on it. It turns out in Venus, once you get below about 60 kilometers altitude, you can put solar panels in any direction because the light is just scattered in all directions. So that's an option, coupled with batteries to maintain some power at nighttime. But also this wind shear I was talking about that blows the tow body downwind also presents an opportunity for putting a little wind turbine on the tow body itself where we can generate power from the wind shear itself. The alternate concept is to periodically retract this tow body like a fishing reel back up to the gondola where it can essentially dock and recharge its batteries for its next campaign. So there's a few options we're playing with in terms of power, but the EVE concept is highly complementary because we would like to increase our coverage of the surface, and every time we go down, we get more and more data. So EVE allows the balloon to live for much longer through the gas replenishment that you heard about. Well, now the tow body could take many more trips below the clouds because the balloon would just be there that much longer.
This solves so many problems. I mean, I know that we've, as humanity, have managed to send some things to the surface. They did not last very long, but I loved those Veneer emission images. And to get more of an understanding of what's going on Venus would be very helpful in this moment. I'm particularly intrigued by the idea of current volcanism on the surface of Venus. We do have some evidence that that might be going on, but how could this help us answer more of those questions?
Yeah, so we'll actually be imaging at nighttime and in the near infrared spectrum. And so we will be very sensitive to seeing any hot spots that might exist through active volcanism, as well as the differences in mineral composition through how they emit near infrared light at nighttime. So while the concept imagery all share all is in the daylight because we have to see the thing, remember that this is actually going to be imaging at nighttime in the near infrared wavelengths we don't quite see, but where the surface of Venus really exposes its volcanic features and potential active hotspots.
Are there any other things about Venus that you'd be particularly intrigued for this thing to teach us?
Yeah, well, there's so many things, especially even the nature of the atmosphere itself is also a component of this mission. We focus mostly on the imaging, but actually getting through the clouds allows us to sample the gas composition through the clouds. And there have been some debates in the literature about the detections of phosphine and its potential implications for as a biosignature. And while I don't think anyone expects there to be existing life on Venus, there could have certainly been a history of life on Venus. And I think both imaging the surface as well as sampling the composition of the clouds themselves could really help to address this astrobiological question of did Venus once look like Earth and harbor life?
Is your team considering what kind of detectors and instruments you would need on board and actually to, not just collect the sample, but actually do the analysis?
Yeah, on the tow body itself, we would have some surface-mounted MEMS compositional sensors, which actually can be these little postage stamp sensors on the outside of the device. They actually prefer to be hot, so they can operate at these hot ambient temperatures we'll be down at, as well as more typical meteorological instruments like pressure, temperature, wind direction, those sorts of things to help us get a better physical measurement of what the atmosphere looks like on Venus.
One thing that really inhibits our ability to do a lot of this science is the fact that it literally rains sulfuric acid in some of the cloud layers up there. How is your team trying to deal with that issue? Yeah, we certainly have to take that into account in terms of our materials selection. A lot of our instruments will be, housed inside of a housing, but certainly the materials exposed to the clouds have to be resistant to sulfuric acid, high UV. So we're, looking into the material selection that are intrinsically resilient to those kinds of species. Yeah. How did you end up working on two projects that were so disparate in topic from each other? Yeah, well, in space robotics, it's really, I think of it as a fusion of many different fields and plugging in together different kinds of technologies to solve a system-level problem. And that's really what both of these concepts are. Me pulling from my prior experiences on different projects to really fuse a concept that's not intrinsically new, like a quantum sensor, for example, but it's a fusion of different concepts that when combined can bring a new capability to a body. So they're all similar in the sense that they're robotic systems for space, and they pull my background from my knowledge in different fields, but obviously for very different applications.
We'll be right back with the rest of our NIAC Symposium coverage after this short break.
For over 45 years, members of the Planetary Society have teamed up to crowdfund science and technology projects like LightSail, the 100 Earths Project, PlanetVac, and so many more. The STEP grant program continues that concept, but uses an open call for proposals to cast our net far and wide to find the best projects. The first two rounds of STEP grant winners have done great stuff, ranging all the way from developing a new technique for studying near-Earth asteroids to doing a careful comparison of different ways to grow edible plants in space. We're once again going to invite the brightest minds worldwide to discover the next breakthroughs in our third round of grants, and we need your help. This vital scientific research will be made possible with your support. Right now, funding cuts at NASA and the National Science Foundation are threatening scientific research. There's never been a more urgent time to support independent scientific funding. This is real space science and technology funded by you. Donations given today will go directly to the next round of STEP grant winners. Please join us in this crucial endeavor by making a gift today at planetary.org/step. Thank you.
Our next guest continues with this idea of mobility as the key to exploration on other worlds. Dr. Justin Yim is an assistant professor at the University of Illinois Urbana-Champaign. He leads the Legged Exploration Across the Plume project, or LEAP. His team is developing a lightweight jumping robot designed for Saturn's moon Enceladus, where geysers are blasting material from the hidden ocean into space. By vaulting directly through those plumes, the robot could collect pristine samples that could teach us a lot about its subsurface ocean and potentially its level of habitability.
I'm here with Justin Yim. You're an assistant professor at the University of Illinois Urbana-Champaign, but also I hear that you run the Novel Mobile Robots Lab while you're there. So your project is called LEAP. It's this legged exploration across the plume, and plume is a dead giveaway, right? We're talking about Enceladus, the moon of Saturn. Where did this idea come from? Was it because of your involvement in this robots group that led to this idea?
Yeah, so Novel Mobile Robots Lab is the name of the organization that I've set up at the University of Illinois Urbana-Champaign. But before that, actually the origin of this project began at University of California, Berkeley, where while I was a PhD student, we got to develop these really cool jumping robots. My lab mate, Ethan Shaler, is another NIAC fellow at JPL, and he'd had this idea from the projects that we'd worked on when we were both PhD students, like, hey, jumping on other small bodies could be really awesome. And, it's taken a little while for us to get to this phase, but we're really excited that now we can explore more of that with NIAC, looking at if we can take some of those jumping robots like I developed during my PhD and I'm now working on in my lab at University of Illinois. Could we get robots that could be really capable of moving around on these bodies with lower gravity?
Well, first off, University of Berkeley, my alma mater, so go Bears. Go Bears. But also, so you're deriving this technology from this other robot at Berkeley. It's called Salto. Before we establish what LEAP does, how does this thing work?
Yeah, so Salto is a very small jumping robot. It's got one leg that extends about 6 inches in total, and that propels it to jump pretty high on Earth. This robot's capable of jumping about 3-4 feet high, and not only can it do that, but because it's got some additional motors besides the really big one that drives the leg, it has 3 more motors that allow it to change its angle in the air. The first big one is this reaction wheel on the side that allows it to tip forwards and backwards, like in a running motion, and then has 2 little propellers up on top that give us control over what's called the roll angle, side to side, and the yaw angle, kind of like the steering, which way it's pointing. So putting those together, since it can change which direction it's pointing, it can bounce like a pogo stick and hop. In this case, we've tested it up to, I think it's like 800 times in a row on a single battery charge, lasting about 10 minutes. And this allows us to get a pretty good amount of distance and a pretty good speed for a robot that's not super, super big. Particularly when you have a small robot, it's nice because you don't have to store as much of the robot. It's easier to pack, it weighs less, it's cheaper to send to space, for example, and on Earth it's just less hazardous to have around you. Downside to being small, everything in the world looks huge compared to you, and you got to get over the same size things as anybody else of any size. In space, it turns out that being small is nice, as I've mentioned, and we still have the same large obstacles, but jumping can get you really far when gravity gets a lot lower. So Salto hops around pretty well on Earth, and we're hoping this could be something that could be really, really good at other places too.
Well, all right, so we've established what Salto is. How is this fundamentally different in its design from the LEAP concept that you came up with? Because this one has you can clearly see it's got wheels on it. How does this thing work?
So LEAP is different from Salto in a few ways. The first one being it's a lot bigger. Salto is only about 100 grams, a quarter pound or so. LEAP is a full 2 kilograms. It's about 2 pounds, which means that it's more capable of carrying stuff, computers, cameras, sensors, things that we'd need like that. And so that's one of the first things we did. We scaled the robot up some amount. The other one that you'll notice first is that while Salto has that one reaction wheel on the side, LEAP now has 2 of them, one on each left and right end, and that are at different angles. This is because because as we saw in Salto, we've got those propellers that change its angle. That doesn't work so well when you don't have an atmosphere, as Enceladus does not. So instead, we use these two reaction wheels to change the angle of the robot. If one of these spins this way, that tips the robot in this sort of diagonal forwards and left direction. And if we spin the opposite one, then we tilt the robot in sort of diagonal forwards and right direction. This means we can control both the front, back, and the left-right lean in order for the robot to point its leg in the desired direction and land or hop the way that Salto does. The extra nice thing about these reaction wheels, though, is that because they are these large objects on the outside of the robot, they're the first things that'll hit the ground if the robot falls over, either intentionally or unintentionally. And at that point, then, the robot can roll on these like regular just wheels, right? And that means the robot can drive around kind of like a little car if we need it to operate in a rover mode on terrain that's maybe easier to get over or flatter or harder or something along those lines. But it also means that the robot can sort of like do a nosedive and do a wheelie to get back upright if it gets knocked over. There's some additional things we'll be adding to these wheels and or like tires and bumpers and so on. But since this is a phase 1, we're only about halfway through that part. We haven't gotten all the features on this that we hope to eventually.
Well, first off, thank you for bringing visual examples so that we can see these things, because that is so much fun. But also, tell me how exciting it is to test out these things with other people on your team.
Oh boy, it's so much fun. So my graduate student, Neil Wagner, has been putting a ton of work into getting this robot ready in time for us to show this at the symposium. And just a couple weeks ago, as we were preparing for the presentation videos, I got to go out with him with a video camera and like record the robot attempting to run around on campus, hopping over curbs and so on. I've got one of those videos in my presentation coming up 11:30 a.m. on Thursday, tomorrow. And so I'll be excited to show everyone some of those videos of the tests then.
We spoke a little bit about how high Salto can hop here on Earth, but clearly Enceladus, different body, a lot smaller. How far are you expecting, or even how high are you expecting to be able to hop with this thing?
Yeah, Salto can hop about 1.2 meters on Earth. LEAP, we're looking at a similar size scale, 1 to 2-ish meters is the height range. On Enceladus, the gravity is 1/80th as strong as on Earth. And conveniently, jump height compared to gravity just scales linearly. If the gravity gets 1/80th as large, your jump height gets 80 times higher. So that means that these robots could jump something like over 200 feet high and over an entire football field 100 meters in distance in a single bound, which could mean that we could cover, of course, really large obstacles you might need to get over. Could be ridges or crevices or other just terrain we don't want to deal with. And it also means that we could get a pretty big distance even on a relatively small battery charge.
Well, speaking of battery charge, you said that the Salto one over 10 minutes hopped like 800 times, right? Mm-hmm. But at some point you're going to run out of battery power. How are you expecting to power this contraption?
Out in Enceladus, we're pretty far from the sun, so we can't use things like solar panels. Instead, we're probably going to be relying just on battery power. This is a mission that we plan would be part of a larger one. Enceladus Orbilander is a proposed mission to have a probe orbit Enceladus and then land at a certain location. It doesn't have any method for getting to the plumes that release those jets of water on the surface directly. It would be collecting particles that are falling down, but it wouldn't be able to go directly to the source. And our thought would be if we could augment a mission like that with a small, lightweight package that weighs about as much as another instrument on that lander, we could then have these deploy from that sort of mothership in order to go and directly sample at the plume locations. So for this, the robot would be charged up from its batteries on the Enceladus Orbilander or a similar mothership, and then travel out to the plume to go gather direct samples at that site. This could either be a one-way mission, or potentially, as kind of a stretch goal, we could see if we could also come back to the lander again and then recharge.
That'd be really cool, just like set down a little induction charger or something, just like nestle yourself in.
Yeah, in fact, I'm chatting with some other of the fellows here. I've heard that there might actually be wireless charging solutions that could be feasible in this area, and we'd love to look into those more.
Why is it that Enceladus is such an important target for us to be able to do this kind of work? Not just for landing there, but hopefully for being able to be mobile and jump through these plumes.
Yeah, Enceladus is a really exciting ocean world. It's one of these other places where there is liquid water. Unfortunately, it's not on the surface. Enceladus is also an icy moon, so there's a thick crust that's covering a lot of this. But uniquely, we know that there's a plume that's cryovolcanically releasing some of this ocean material out into space. Because there's an ocean there, and we have also, from the Cassini mission, seen that there are organic molecules and energy sources that mean that we've got the ingredients that life needs, it's a really high candidate for potential locations that life could be in our own solar system, besides on Earth. And because this plume is there, not only is it a great candidate for life, it's also a place where we could go and search for the those types of things, like the chemistry and the workings of that ocean, by just looking at things on that surface that's being, essentially blasted into space for us to analyze right there for us naturally. If we can go and get to the plume at the source, down to the surface where the jets are being emitted, we can get more information about how those jets work, what's causing them to be erupted out into space, and also how the ocean chemistry varies from place to place. If you're just collecting in some location from all of the jets around, you don't know as much about that kind of spatial variation as well, and getting those direct samples allows you to get more of that information. Furthermore, as another stretch goal, if we are able to come back to the mothership lander and recharge batteries, we could also try to do things like bring back pristine samples to the lander as well. This would allow us to capture those before there's any weathering, and could get us some more information there too. Again, if we can get that stretch goal of getting back to the mothership.
But, there might be a bunch of water erupting out of these plumes, right? So how are you going to account for potentially how those plumes might interact with it, given that, there's a lot we don't know about these plumes, what the pressures of the water, how much water is coming out?
Yeah, that's right. So this is something that we were pretty concerned about at the beginning. Of course, these plume materials are getting all the way out to space, which means that they're reaching escape velocity for at least some of these things, and we don't want our robot to be leaving the surface. And so we were worried about, are we going to have disturbances from these jets? However, because they are really, really diffuse, super, super low density, though the speeds of some of these particles are quite high, the total force that will apply to the robot that weighs a whole 2 pounds, 1 kilogram, is very, very low. And so at least from our basic calculations at the beginning, they're so small, they have almost no effect. And that means that we don't have to worry too much about being overly disturbed by the jets as we're jumping through them to collect measurements.
Over time, are you worried about ice buildup on the robot? If it's jumping through it multiple times, at some point, conceivably, it might ice over.
Yeah, ice buildup is an interesting question. There's a potential of picking it up in the plume, but there's also a potential of just picking up while we're on the surface, since we'll be rolling in the ice particles and ice that is on the surface. So that's something we have to think about, how that's going to change the mass of these things. There are a couple things that we might do. One of them is that these reaction wheels do spin relatively quickly. There may be a chance to shed some things that way, but that's something we'll have to look into more, certainly.
So you're conceiving potentially of putting some kind of sample collection mechanism on here. Is that the kind of thing where you'd only be able to take one sample and then take it back, and then you wouldn't be able to collect another sample because of contamination? Like, would that become an issue for understanding what's going on with that water chemistry?
Yeah, all right. So there's multiple ways that we're thinking of doing sampling. Some of it's going to be just taking direct measurements, things like pressure, things like particle flux, that we'll be using sensors to collect, and we won't then have, those sensors will continue to operate as we hop through the plume at multiple different locations. And that will allow us to get a bunch of different measurements at different locations. If we wanted to do something in that sort of stretch goal area where we'd bring back a sample to Enceladus Orbilander, then I don't know if we have worked out exactly what the ConOps look like for that, but it might be something like we do this just the one time. However, because LEAP doesn't weigh too much, our plan is actually to have several of these robots go in a team. That means we have both multiple chances to collect samples with each of these robots and the chance to sample at multiple different locations if we sent a few robots to a few different spots.
I'm guessing you're probably not going to be able to put all the sample analyses instruments on LEAP. So are you conceiving that Orbilander or some other spacecraft would be doing all that work for you?
Yeah, I think that the main system would be doing a lot of the heavy lifting. If we want really detailed analyses, then the larger instruments that would be required for that would fit on something like Enceladus Orbilander instead of on the much smaller LEAP. However, as part of our initial phase 1 study, we've been looking at the availability of smaller scale sensors that may let us do a few of those measurements on a system like this. We found there are MEM sensors that can do things like temperature and pressure, as I've mentioned, but even a very small mass spectrometer using MEMS technology that might allow us to do some analysis of the makeup of what's in the plume as well, using this one, but probably not the same type of high resolution and scientific capability of a larger system.
Now it's time for What's Up with Dr. Bruce Betts, our chief scientist at the Planetary Society. This week, we're going to take a closer look at those gravity poppers we mentioned earlier, and why on some small asteroids, a simple hop could send them flying right off into space instead of landing back on the surface. Hey, Bruce.
Hello, Sarah.
So one of the stories that we had at NIAC this time around was actually, planetary defense related. They had these cool little things they called gravity poppers. And I think the idea is basically you just put a bunch of tiny little hopping robots on a small body to try to do gravity sounding and figure out what's going on inside. But they did mention during one of the talks that they gave, that their presentation, that if you try to get these little poppers near the equator, you're probably going to lose a bunch of them to outer space. So I figured I'd ask you, why is it so probable that if these things hopped from the equator of one of these small bodies, they're likely to fly off into space, whereas if you tried it at, say, like the poles, it wouldn't be as likely?
It's because gravity goes as the square of distance from the center of mass, and because these asteroids are spinning just like the Earth or all the planets, they're spinning. You end up with a force pushing out the equatorial region, so it puts the equatorial surface farther from the center. Therefore, the gravity is somewhat lower. Now, that's not a huge deal like on Earth, although you can measure it, but it is kind of a huge deal when the gravity is so low already, particularly for small asteroids. You're barely staying on the surface, depending on the size of the body, whether it's hundreds of meters or a few kilometers matters quite a lot. But the escape velocity is very, very low, and so you could have this situation where your popper is okay popping not near the equator, but near the equator, it's because of the spin, and because of that has bulged the surface out as well. You get a combination that can launch you off the surface, or not. It depends again on the mass and size and what's happened, and whether you design your popper carefully enough to keep yourself on the asteroid.
Why are these things spinning so quickly that this becomes an issue?
Probably because a lot of them are ice skaters, and
they pull their arms in.
Exactly, but especially the smaller asteroids tend to speed up over time, and it's partly due to the Yorp effect. Yes, that's right. It's either a camping snack, or it's the Yarkovsky-O'Keefe-Radzivinsky-Paddock effect, which is tied to just the Yarkovsky effect, which we may have talked about before. Basically, it's the concept that when you heat one side, the sun heats one side of the asteroid, and then as it rotates around, it radiates some of that heat, some of those photons asymmetrically on the night side. And so you end up changing the orbit slightly, but you also can end up spinning up the asteroid, again, over very long time frames.
I think my ideas on asteroids really changed when I stopped thinking about them as just these giant hunks of solid rock that was always depicted in movies and stuff from my childhood. Thinking of, what these rubble piles can do, and then seeing all these weird potato double-lobed ones definitely changed the way I thought about them entirely.
Yeah, we got the double-lobed ones, but then we got the ones that I did a poor job of describing, and there are some themes in what we've seen so far. And so even though you first look, hey, they all look like gray, boring rocks. There's some interesting, weird stuff going on. And there's a lot of variability, which is one of the interesting things for science and challenges for planetary defense, because you have ones that are literally, at least mostly solid metal that have been basically come from an object that was big enough to differentiate and have the iron and stuff get sucked down towards the center, and then they get broken apart, and you end up with about, I think it's 4 or 5% of the meteorites we get, for example, from asteroids are metal based, but most of them are rock based. But there's variability. But then there's variability in the physical properties, which you alluded to. So you've got ones that are very solid. We've seen now rubble piles like Bennu, where material even was getting thrown off of that are barely held together by gravity, lots of chunks. And there may even be the official term, I kid you not, fluff balls, where you get a lot of very small stuff stuck together, probably combined with a rubble pile thing.
So if you get, fluff balls, then they evolve into ball pits, and then, okay, that's random.
I like random. And this week, we're going to go back to Random Space Fact Rewind. Facts so good, we're revisiting them. That's right. A fact from the past. One of my favorites of an example of what I mean by random space facts and things that give you insight into the universe in some different way. And here we're talking Mars. And the surface area of Mars is about the same as the land surface area of Earth. So if you remove the oceans. So here's the interesting implication. You think about us sending spacecraft there, and we've had a couple rovers here and a couple rovers there. It's the equivalent of trying to explore the entire land surface of the Earth is the challenge we have in exploring Mars.
We're going to need a lot more rovers.
We're going to need a bigger rover. No, that's a bigger boat. We definitely don't need a boat. 3-4 billion years ago, sure. Probably a lot of Martian boats floating around, but not now. All right, everybody, look up in the night sky and think about taking a raft down Ma'adim Vallis on ancient Mars when the water was flowing. It'd be crazy, man. Thank you and good night.
We've reached the end of this week's episode of Planetary Radio. But we'll be back next week with Dagomar de Groot, the author of the new book, Ripples on the Cosmic Ocean. If you love the show, you can get Planetary Radio t-shirts at planetary.org/shop, along with lots of other cool spacey merchandise. Help others discover the passion, beauty, and joy of space science and exploration by leaving a review or a rating on platforms like Apple Podcasts and Spotify. Your feedback not only brightens our day, but helps other curious minds find their place in space through Planetary Radio. You can also send us your space thoughts, questions, and poetry at our email, planetaryradio@planetary.org. Or if you're a Planetary Society member, leave a comment in the Planetary Radio space in our member community app. Planetary Radio is produced by the Planetary Society in Pasadena, California, and is made possible by our members from all over this beautiful planet. You can join us as we help support the big ideas that are going to make space exploration even more amazing in the future at planetary.org/join. Mark Hilverda and Ray Paoletta are our associate producers. Casey Dreyer is the host of our monthly Space Policy Edition, and Matt Kaplan hosts our monthly Book Club Edition. Andrew Lucas is our audio editor. Josh Doyle composed our theme, which is arranged and performed by Peter Schlosser. My name is Sarah Al-Ahmed, the host and producer of Planetary Radio. And until next week, Ad Astra.